welcome. I'm Emily Conover, senior physics writer for Science News. In honor of the 100th anniversary of our publication, we are interviewing some leaders in science on some big questions. I am delighted to be tackling the topic of black holes with Dr. Andrea Ghez, an astrophysicist at UCLA and notably a winner of the 2020 Nobel Prize in Physics for her work that unveiled the supermassive black hole at the center of our home galaxy, the Milky Way. Thanks so much for speaking with me, Dr. Ghez.
Oh, it's a pleasure to be here.
So, I think it's fair to say that black holes are having a moment right now. On top of your own research and the Nobel Prize, we have the gravitational wave observatories, which in 2015 first spotted two black holes spiraling together and merging. We have the first image of a black hole silhouette from the Event Horizon Telescope in 2019, and lots of other, too many exciting results to mention. So I think it's really fitting that we're talking about this topic today and right now. And I thought maybe to start, for our viewers who might be less familiar with black holes or might only know them from science fiction movies, can you start by just defining what a black hole is?
Sure. Black holes are remarkably simple given the fact that they really push our understanding of physics forward, or challenge our understanding of physics. So a black hole is very simply a region of space where the pull of gravity is so intense that nothing can escape it, not even light. You can also think of it just as an object whose mass is confined to zero volume. And so the idea of density, which is mass divided by volume, that goes to infinity. And that's like the big giant red arrow that says you don't have your description of physics correct right here.
Yeah, and that's sort of where all the weird puzzles come in, right? And your work in particular, you focus on supermassive black holes, one supermassive black hole in particular. Can you talk a little bit about the distinction between these sort of supermassive giant guys and the smaller black holes?
Sure. I mean, in astrophysics, we think of two classes of black holes. And in fact, these two classes nicely demonstrate the two ways in which science is often done. So the first ones that were recognized or understood are what we call the stellar mass black holes. And they're the outcome of how stars that start off their life as very massive stars with more than 30 times the mass of the sun are expected to end up. So predicted by theory and demonstrated beautifully observationally with the gravitational wave detectors. The supermassive black holes are much more massive, as the name suggests. So rather than being on order of 10 times the mass of the sun, they're more like 1,000,000 to 1,000,000,000 times the mass of the sun. And we think that they reside at the center of galaxies, so that each galaxy is thought to form with one central supermassive black hole. So these were found observationally, and now we're on the hunt to understand theoretically how they formed.
One thing, about both types of black holes, there's sort of this nexus of lots of these really big questions in physics and astronomy, and they cover sort of a variety of different sort of subfields, right? So you have fundamental tests of general relativity, which is Einstein's theory of gravity. Questions about how galaxies form, everything in between, right? So I'm curious what you think. What is the reason that black holes in general are such fruitful grounds for research on such a variety of topics?
Oh, that's an interesting question. I mean, in the case of fundamental physics, which really crosses both the stellar mass black holes and the supermassive black holes, you really have very fundamental questions about how our universe works. We only have four known forces, and gravity is one. It's the one we're most familiar with in terms of our intuition. Here on Earth, you throw a ball up, it comes back down. And yet it's actually the least tested of the four forces. So black holes provide this avenue for furthering our understanding of fundamental physics, and in particular, our inability at the moment to bring together the two fields of quantum mechanics, which is the study of things that are very small, together with the field of general relativity, which is our best description of how gravity works. In the case of supermassive black holes, these things reside at the center of galaxies, where you have extreme environments in many, many different ways. I mean, not only is the gravitational field extreme because of the black hole itself, but the centers of galaxies are extreme in many other aspects, such as the stellar density. So people often refer to the center of galaxies as like the urban hub. It's like the center of New York City, and we're out in the we're halfway out in the galaxy, so we're out in the calm suburbs. But almost any way you can describe a galaxy becomes more extreme. The magnetic fields, the winds, just the activity in general is really extreme. So it means that you have an opportunity to understand the physical processes that are associated with multiple aspects of a galaxy in the extreme environment of the center of galaxies. So in the case of the supermassive black holes, you get that extra layer of trying to understand not only the formation and evolution of these galaxies, which we think the black hole plays a central role in, but just physics, sort of physics of the extremes.
Yeah. That's great. I know physicists always love to look at the most extreme example and use that to test their understanding. So I think black holes are definitely a good example of that. Great. So I'm curious if you could tell us your sort of scientific origin story. So what was it that originally drew you into this topic, or how did you get started with your fascination with black holes?
Origin stories are always complicated, astrophysically or otherwise. So mine, I can tell you a narrative that will make sense, but it wasn't actually as clean as the narrative, which I'll also share. So the family lore is that when I was 4 years old, and I do remember this, the first moon landing was happening. So I got excited about thinking about the universe. Certainly started to stay up late at night worrying about the enormity, the timescales, the boundary, and the family legend is I announced that I wanted to be the first woman on the moon. I mean, today I joke, the job's still open, but I certainly got more interested in pursuing astrophysics from the ground. But at the same time, I also wanted to be a ballerina, as little kids are wont to do. They have multiple ideas about or ways of thinking about their future. So while I got exposed to it early on and was fascinated by it, I wasn't singular or certain in my path forward. But what I do remember, and I think really connects, is that I've always been interested in solving problems. So ultimately, my interest in dance got into choreography, which is basically a problem-solving exercise of how do you put this, this dance story together. And I became very good at math. So I actually went off to college wanting to be a math major. And soon discovered it was much more esoteric than I thought. And at that point was quite interested in black holes. So I switched to physics as maybe more an experimental approach as opposed to a theoretical approach to black holes.
Great. So when you were starting your work, what can you describe for us? What was sort of the scientific attitude towards black holes? Were people confident that they existed, or was there still some question? And then how did your work sort of move that forward?
Yeah, so when I started this project, there was definitely the idea or the notion that supermassive black holes might exist at the center of galaxies. And in particular, the state of the field was that there's a small class, or about 10% of all galaxies have an unusual amount of energy coming out from their centers. They're called active galactic nuclei. I mean, their name really says it all. Their nuclei or their centers are very active. And it was hypothesized that what was driving all this activity was a supermassive black hole at the center. So that would be the central engine. And roughly at that same time, people were asking, could it possibly be true that all galaxies harbor supermassive black holes? And in the case of normal galaxies, these are black holes that are basically on a diet, are lacking material falling onto the black hole, which is how we thought the active galactic nuclei were being powered. But in our case of our own Milky Way, the idea, our galaxy is a ordinary garden variety galaxy, nothing special about us. The idea there is that there's very little gas at the center, and so perhaps this is a black hole that was simply starved. So that really offered, I mean, that's what also introduced the idea that the Milky Way is a great place to ask this, because it's the closest example of a supermassive black hole that we'll ever have to study. The next closest one is 100 times further away. Now, while there was that idea, there were also some counter arguments to the idea that our galaxy could harbor a supermassive black hole, or just that all galaxies had supermassive black holes. And that was that there were very young stars seen in the proximity, not as close as we ended up looking, but out at further distances. So already the existence of these young stars gave some trouble to the notion that there was a black hole there, because black holes produce these very strong tidal forces. So the idea that gravity depends on distance, so that the pull on one side of an object is greater than the pull on the other side of the object, so much so that it just distorts or pulls apart the object itself. And stars, baby stars, start off with as very fragile clouds of gas and dust. So there was this problem already that people said, well, look, there's not enough gas or dense enough gas to overcome this problem. So that's an argument against the black hole. So that's really where the argument was in the early 90s when we jumped in. You know, a nice scenario for why they should be there and an argument against them. So that was really the state of the field. Although I should mention one other thing, which is that we did know that there was an unusual radio source at the middle. Its name is Sagittarius A star. So Sagittarius because it's in the constellation of Sagittarius. So if you look up at night and you look for the constellation of the teacup, it pours into the center of the galaxy. So that's how you can find the center of the galaxy if you're out camping. And A, because it was the brightest radio source, and star because people were trying to be very clever. They were borrowing notation from nuclear physics, where the asterisk meant excited state. So they were seeing gas that didn't look like a star. So it was Sagittarius, really not a star. So it's one of those names that's so we really should say Sagittarius, not a star. So they thought it was like a low, very, 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 very faint equivalent of the active galactic nuclei centers.
Right. So then you come in and start looking at these stars that are very close to the Sag star, which at that point in time was not known whether it was a supermassive black hole or not. Were you able to reveal that in fact that is what we were seeing there?
So the idea of the work that we did was that stars that are very close should provide the most direct evidence for a supermassive black hole through their motions. So if you can discover stars that are there and track their motions, so basically watch their orbits, these stars should orbit the center of the galaxy for the same reason that planets orbit the sun. So it's just gravity, and each orbit tells you how much mass is inside its orbit, and then the size of the scale of that orbit tells you the region that you confine the mass to. So the proof of the black hole is lots of mass inside a very small volume or radius. And in fact, you'd like to get inside the Schwarzschild radius, because that's the point at which gravity overcomes all other known forces and forces that mass to become the infinitesimally small object that we know as a black hole. So you want to see stars as close to the center of the galaxy. So the first challenge was, can we find them? Can we discover them? And since you want to get close, you need to go to wavelengths where you can see the starlight. So radio wavelengths, you don't see much light from the stars. It's mostly dominated by the gas. So we went to the infrared. You can go to the optical or the infrared to see starlight, but at the center of the galaxy, there's lots of dust between us and the center of the galaxy. And that dust is very good at absorbing optical light, what our eye detects. So it's basically invisible at optical wavelengths. But if you go to the infrared, you can see that starlight. So that's why all our work has been done in the infrared. Next, you want to go to a big telescope. the larger your telescope, the better the angular resolution. So you want to see stars that are as close as possible. So it's really important that you get to high angular resolution. So the larger the telescope, in principle, the smaller the scale that you can actually see. And the largest telescope in the world that can see infrared light right now is the Keck telescope. This is out in Hawaii, but it's on the ground. And so you have to contend with the atmosphere. So the next challenge is you have to beat the atmosphere. And so that's what we've done a lot of work on, is trying to figure out how to beat the atmosphere so that you can actually see these stars and track their motions.
Yeah. I have to say that the videos that you've made of showing this data over decades of these stars moving around the supermassive black hole, they are so fascinating to watch. I just love kind of marveling at the fact that we can even see these stars and measure them moving around this, extremely massive black hole. It blows me away every time. So I'm just curious, when were you first able to see that, and what was the feeling that you had when you were first able to do that?
Oh gosh. So this actually goes back to when I first joined the faculty at UCLA. That was in 1994. So I joined the faculty because I really wanted to do this experiment. I wanted access to the Keck telescope. Keck is co-owned by the University of California and Caltech. So this to me was my dream job. So I put my very first proposal in 1994, and it was turned down. So it was turned down because people hadn't done this diffraction limited imaging at Keck yet. So they weren't there. There was a lot of skepticism about whether or not Keck, which is a segmented telescope, could actually achieve diffraction limited resolution, in spite of the fact that it was designed to do so. So it took us a year to convince people that our approach would work. But so we started in 1995 as a result. So the first thing we needed to do was demonstrate that the technique would work. And in I guess we actually did that in 94. We just had to prove that the technique would work. And then in 95, we actually saw the images. So you could prove that they could work. This business works at the center of the galaxy. So that was really exciting in 95. But you hadn't seen the motion yet. So the original approach was just to see how things move on the plane of the sky. So you need 2 images. So we did that in 96. You have 2 points. 2 points determine a line. And oh my goodness, I cannot tell you how exciting it was in 1996 to get that second image. And of course, there are lots of challenges along the way, including the first night in 96 was weathered out. The second night, I think we had instrument problems, and it was the third time we went in and actually got the data. So there's nothing like a little bit of obstacle to make the success even sweeter. We didn't publish until 97 because we actually wanted 3 points to make sure we understood how well we were doing, because of course there are lots of challenges associated with making these measurements. So it was 97 that we submitted our first paper on doing this. I'll say, actually, I can say a little bit more about that phase, which was also really fun, because we only thought we were going to do a 3-year experiment.
Wow.
So the original idea was just to get the velocities, because you can prove statistically, you can use ensemble averages, or velocity dispersions rather, to get the enclosed mass. But at that point, people were pushing back. There was a lot of skepticism that it wasn't actually a black hole. And the particle physicists got into the act at this point and started suggesting that there were other kinds of objects it could be. And in particular, the idea that it could be a fermion ball. So these are objects that are, I guess they're like neutron stars. So rather than being a pure object of neutrons, these are more primitive particles, which means that it's more compact. And there were also suggestions that these objects, the fast-moving stars that we were seeing really close in, weren't actually bound to the center of the galaxy. It was really fun. I guess it was really fun at this point in the experiment because people were starting to push back on the idea that the velocities that we were seeing were from the black hole. And you can do a freshman physics calculation that tells you that you should be soon seeing the accelerations if this is indeed a black hole. So we just kept going. And soon enough, the things started to curve. And at that point, you can do some, again, simple things. There were 3 stars that showed the first accelerations, and each acceleration should point to where the black hole is, because it's a central potential, and the central potential should be radial. And even in projection, you should get these vectors that point to this is where the black hole is. And so all of a sudden, you actually can show to much higher that this mass is associated with that unusual radio source, Sagittarius star, to very high degree of accuracy. And again, pushes you to the next level, because at that point, you know that the orbit should only be on order of 10 years long. We'd been going for 5 years. What's another 5 years? And at that point, it was clear that we should continue. And people even at that point were starting to anticipate the power of these orbits, and it could show you that not only that there was a black hole, but could introduce new ways of testing Einstein's theories of general relativity. So I have to say that paper, the acceleration paper, which came out in 2000, was really a transformative moment. I think that's at the point that we really understood how much science could come from this sort of work. It was really an exciting moment.
Yeah, and you're still, of course, working on the same area, the center of the galaxy today, right? So, I mean, I guess I'm wondering, do you ever lose interest? I mean, how does this keep your attention for so long, from the 90s until now?
Well, what's been so fascinating about this is there's been such evolution, both in terms of the data themselves, because you keep going, and of course with the game of orbits, time really helps. The power of these measurements increases dramatically with time. But along the way, we've also had the benefit of advances in technology. So after the first decade, we moved from a very simple approach of speckle imaging, which only allowed us to take images at a single wavelength and that were not very deep, to adaptive optics, which was a much more powerful technique and opened up new kinds of measurements. And the most important was our ability to get spectroscopy, which gave us motion along the 3rd dimension, along our line of sight, but also told us what kind of stars we were looking at, which revealed a host of new questions, astrophysical questions. And that, along with being able to take images at different wavelengths, just opened up many new questions. So I think that's part of what's been so fascinating or captivating about this project is the continual opportunities to go in new directions. So while it seems like we've been doing the same thing all the time, or for a long time, more than 2 decades, in fact, the kinds of questions that have been pursued have changed quite dramatically over time.
Mm-hmm. Right. Yeah, going from, is there a supermassive black hole there at all, to can we test, does general relativity apply near the supermassive black hole, and so on, right?
Yeah, today we're looking at black hole accretion physics, we're looking at tidal interactions, we're looking at star formation in extreme environments, we're looking at dynamical interactions. I mean, among other things, and of course the new tests of GR are really exciting, and now we're on the hunt for dark matter. So it's been an incredibly rich adventure.
Well, it's interesting to me because I think naively, you might expect that black holes would be sort of a dead end because they're black and you can't see inside them, so you don't know what's going on, right? But we've had so many interesting observations, right, to reveal more details of these objects in all these different inventive ways, right? So I'm curious if you have any thoughts about how we've been able to make so much progress, and do you think that people, when black holes first appeared in physicists' minds? Do you think people expected that we'd be able to understand them as well as we do now?
Well, that's an interesting question about what people understood. I mean, I think scientists are incredibly optimistic in general. Uh, I think um, there's always I mean, I think for a long time there's an understanding that technology is always going to drive your understanding of science further. Um, so who knows? I mean, it's I'm sure they didn't imagine where we are today. I mean, we didn't even imagine where we were today when we started this experiment. So, half a century ago. But that's one of the wonderful things about science is it evolves so quickly. I mean, especially in astrophysics. I mean, if we think about how far our understanding of the universe and all the phenomena that are in it have evolved, it's rather remarkable.
Yeah. Yeah, it seems to be one of those situations where black holes are just so fascinating to physicists that they throw everything, every technology, every tool that might be useful at understanding them, and then we get some really cool science out of that. So, well, as you mentioned earlier, when you were doing your measurements and when you're beginning to do these measurements, no one had ever done them before, right? I'm curious if you ever felt like you were on the wrong track, or you worried that you might not succeed. What was that like for you?
Oh gosh, yes. I mean, quite frankly, I wish I had kept a diary through this whole experiment because it's been, I guess today, 27 years of lots of highs and lows and uncertainty and delight all along the way. And there are definitely ebbs and flows throughout this whole project. I think there was a time right before adaptive optics came online, and we were still in the speckle mode, where that wasn't, in some sense, it's like we were getting to the limit of the return for speckle imaging, and I think that was an interesting lull. We did know adaptive optics was coming, and we were pushing forward on that front. But it's always scary before a new technology actually becomes scientifically productive. Is it actually going to deliver the promise? And I'd been working with adaptive optics for 15 years before it became scientifically productive. So, you're never sure. So I think that was one of the really exciting things about the Keck system is that unlike a lot of earlier systems, it really was well designed in terms of doing something that was technically robust and scientifically mature rather than being just another step in terms of technology development. It became scientifically productive.
You touched on this quickly earlier, but I wanted to give you a chance to go into a little more detail about some of the new questions that your research has opened up, and what big puzzles kind of await that you're looking at.
Oh, there's so many. I mean, I love working with new technologies because new technologies give you this very different view on the universe. And often you're quite surprised when you look at something in a new and different way. So some of the first problems that we're still pursuing actually hark back to the original questioning about supermassive black holes from the young stars. So some of the closest stars that we've discovered to the supermassive black hole are actually young. So this exaggerates some of the early concerns or the tension between the existence of a supermassive black hole and the existence of young stars. So the densities that you need to overcome the tidal forces from a black hole scale as your distance cubed. So if you bring your young stars that you've discovered from being quite far away to where we are today, the densities required are roughly 10 to the 8th times higher that you need to overcome the tidal forces than are seen today. So I call that I call that the paradox of youth. So understanding how you get young stars in this extreme environment is a really intriguing problem. And it's been super interesting because people have produced theories for explaining this from all different angles. It's really it's inspired a lot of theoretical thinking, and in three fundamentally different ways. So one idea is that these really are young stars, but you form them far away where the tidal forces are really low. So that requires you to think about a dynamical process that brings these young stars in really quickly. So you need some sort of express bus in terms of physical processes for migrating them in very quickly. And that's actually quite difficult to do. And you have to invoke an intermediate mass black hole between the supermassive and the stellar mass black holes. So they may exist, but we have yet to really have ironclad evidence. So that's a possibility, although lots of questions. Another idea is that maybe these things that we're seeing as young stars aren't young stars, they're old stars, which are masquerading as youth. And the idea there is that old stars have had lots of time to form someplace else and migrate in. So that's certainly a possibility. And then the third possibility is that these are young stars that really formed where you see them, so in situ, and that the gas densities when they were being formed was much higher, by the 100 million times higher than we see today. And as we kept making our measurements of orbits, there was an important signature that evolved for these young stars that were distributed through this central region, which is roughly half of the young stars seem to reside in a disk, so have orbits that all lined up. So in fact, it looks a lot like a scaled up solar system. And so, in fact, you can borrow some ideas from planet formation or the formation of our own solar system, where some of these planets might have formed out of an accretion disk that existed at the time of formation. And in fact, this is the most popular idea today for explaining the young stars at the center of the galaxy, is that our galaxy might have had a very thick accretion disk a few million years ago, which would not only have formed these young stars, but also could have supplied a reservoir of gas to accrete onto the central black hole, making our black hole seem much more like of an active galactic nuclei than it does today, suggesting that the whole galaxy was much more active in its youth than it is today. Another mystery is surrounds the old stars. The old stars, as I mentioned before, should be congregated around the black hole and should form something called a cusp, but an enhancement of their densities. The local concentration of old stars should be great near the supermassive black hole. And in fact, we look for that concentration of light that comes from that enhancement of the crowding in other galaxies. But we don't see that in the old stars. We actually see a dearth of old stars at the center of the galaxy. And so that's been yet another mystery. How do you explain this phenomena that we think is a prediction of having a supermassive black hole at the center of a galaxy that we rely on? And that might have to do with, there's, again, a couple ways out. These either something dynamically perturbed the galaxy in the recent past. So maybe we accreted a small galaxy that messed up this local concentration. Or these old stars that we can see were stripped of their outer atmospheres, making them seem faint. And then the last idea is that the cusp resides in objects that we can't see. This is called the dark cusp problem. And that's an intriguing idea that we're now trying to sort out with the measurements of stellar orbits, because that dark cusp should actually impact the way the stars orbit. So that is a second very intriguing idea. the third that I'll share, and I'll stop there. But there's countless other directions. Is a class of objects that are that were not predicted. There were no predictions for these, like unlike the young and the old, where we had clear predictions. These are objects that, when they come through their closest approach with the black hole, they seem to be tidally distorted, which is incredibly fun. To be able to see things evolve over time. So not only do we see stars orbiting on a human timescale, but we see these stars become tidally elongated as they get near the black hole and then become compact again. And this is surprising. And this was only with the advances of the ability to see images and at different wavelengths, at longer wavelengths, as well as the spectroscopy. And what we think these are objects that merged. So most stars are actually formed as binary stars. If you put a binary star near a black hole, you get a three-body interaction. And that three-body interaction could cause the binaries to merge. And during that merger process, what happens to the star is it gets bloated, gets really fat, about 100 times larger than the other stars that we see, the more typical, the more anticipated stars. And as that very bloated star goes by the black hole, it's large enough to experience these tidal interactions and have the outer shell affected by the black hole. And that's exciting. This one I find super intriguing because it may be lighting up a process that may explain one of the mysteries associated with the gravitational wave experiment. So in LIGO, LIGO and Virgo, they're seeing objects that are more massive than they expected. So stellar mass black holes that are 30 times the mass of the sun rather than 10 times the mass of the sun. And also at occurring at a frequency much higher than they expected. So most stars are concentrated towards the center of galaxies. And if you think this three-body interaction is driving merger events, and mergers are the underlying phenomena that you see with gravitational waves, you may be lighting up a process that's really important for explaining the source of gravitational wave emission. So it's not that we're seeing black holes merger products, but a process that could be driving stellar mass black holes that would also reside at the center of galaxies. So I'm intrigued by that because it's like when you see something that you don't expect in one field, providing maybe a clue to an unexplained answer in another area. That's like unlocking multiple secrets. So I'm intrigued by that third problem that we see today.
Yeah, that's really fascinating. I love how, and this is sort of what I mentioned at the beginning, is that these black holes, the questions, connect to so many different other areas of research. And it's also just so fascinating to me that we can use this kind of research to understand what our galaxy was like in the past, understand the history of where we are and what our galaxy was like before. Just so many big questions. It's really fun, really interesting.
It has been. It's been an amazing journey to understand what we can understand at the center of the galaxy. And I think we have a lot to be thankful for in terms of the remarkable progress that's been made technologically that's opened up our ability to see this really fascinating region.
Well, I'm curious what you think our future conception of black holes will be. I mean, will we have to revise what we understand about them as we keep learning more, do you think?
Oh, absolutely. I mean, I think as scientists, we're so drawn to things that we don't understand, where our models are limited, because those are the places where there's the most opportunity to advance our understanding of physics. So black holes definitely represent the limitation or the frontier of our knowledge. And without a doubt, we will be making progress. There are so many new technologies that are emerging at the moment, not only with our ability to see the stars with adaptive optics, with our ability to see gravitational waves, through LIGO and Virgo, as well as the Event Horizon Telescope. But we have LISA to look forward, the space-based gravitational wave detector, which should open up the ability to study the supermassive black holes with gravitational waves, where the ground-based gravitational wave experiments are really focused on or sensitive to the stellar mass black holes. So I think that will be remarkably exciting. And then in my own area, I'm extremely excited about the next generation of large ground-based telescopes, so the 30-meter telescope, and as it will allow us to see the full population. I mean, today we can only see the brightest stars at the center of the galaxy. And the way I like to explain what I think the potential is it's like trying to understand the economy by only being able to see the largest transactions, which are big but few and far between compared to the smaller but more frequent interactions. So same things with the stars. There are lots of faint stars and very few bright stars. So today we can only see the brightest stars because they're separated by larger distances. And the fainter stars become lost in the confusion of the stellar density. So at higher resolution that these next generation telescopes should afford us, we'll be able to see beyond the tip of the iceberg and see those common everyday stars. And in particular, we'll be able to see stars like the sun to understand really the full range of activity that resides at the center of the galaxy.
Well, that's very exciting. It seems like there's a bright future for this kind of work. I'm curious, what's your advice to young people who are fascinated by black holes and want to go on to study them?
Oh, my advice to young people in general is find out what excites you, where your passion is, and pursue it. Anything that's interesting is going to be hard. Interesting and not already done is hard. So when you have passion for something, that it'll motivate you to overcome the inevitable obstacles that you'll face along the way.
Andrea, thank you so much for talking with me. It's been really fascinating. And for the viewers, you can keep up with the latest discoveries in astrophysics by visiting us at sciencenews.org and connecting with us on social media. Thanks for joining us.